All right, we're off and running, it looks like. All right, just a few housekeeping items before we get started, of course. By the way, I thought lab went fine yesterday. Hopefully everybody else did as well. Any issues, any comments, concerns, anything like that that you can think of from yesterday? I think it went fine. So again, let me know if there's anything there that you think we guys need to discuss. All right, just a couple of other things. I did post a couple of things up to D2L for us for the upcoming week. So I gave you guys hard copies of the next lab, which we're going to start next week, of course. And I also posted that up at D2L. So you can either use the hard copy I gave you, or you can grab a copy from D2L. It's there at the course site. The other thing I did was I put up the next homework assignment as well. So we should be able to work on that and get it done by next Tuesday as well. Again, for whatever reason, if we stretch beyond that, I'll just extend the due date out. I'll let you know. But for now, assume homework number 2 will be due next Tuesday in lab. Also, the other thing due on Tuesday in lab will be your yellow pages from the lab you guys did this week. Okay, so I think that's all the housekeeping stuff we got to get out of the way. All right, any questions or comments on that? All right, good. So let me pop out of here real quick, guys. I'm going to go over to my notes. And we're going to start up a new set here. So these are going to be, what is today, the 17th? All right. Everybody hear me okay? You guys are really, really quiet.
Yep. Yeah, you good.
Just want to make sure. Sometimes when I hear silence on the other end, I'm just never quite sure if Zoom's dropped me or something like that, and that does happen.
No, you're good. Are you sharing right now? Because I heard you writing, but it doesn't look like your screen shared.
Yeah, thank you for telling me. I may not have hit the screen share. I probably didn't. So let me pop back to Zoom here real quick and do that. Yes, I did forget to do the screen share. Thank you, John. That was you, I think. Yes. That's the thing I have to make sure of, is that you guys can see what I see and that I'm actually recording. Yep, I think we're good now. So let me pop out of there and back out to my notes. Here we go. And that's where we're at. All right, folks. So we got through statistics and all of that good stuff. So really a lot of what we've talked about up to this point in lecture is kind of nuts and bolts stuff that we're going to carry throughout the course. It's kind of those basic skills you're going to need that you're going to be using all the time. Okay, so when we talk about accuracy and precision of glassware and measuring devices and application of statistics and types of error and all that, that's stuff we're thinking about pretty much in any lab that we walk into. So what we want to do now is we want to start talking specifically about items that we're going to need for specific labs. So the way the lecture part of this works is I'm going to start prepping you now for the lab that you're going to be doing for the next 3 weeks. Okay, so it's the gravimetric analysis of calcium as calcium oxalate. So there's a lot of chemistry involved there that we're going to talk about. And we're also going to talk specifically about the experiment as we get a little closer to it and we actually start into it. So that's really what we're going to be on to for the next maybe week or two. All right. So we're always going to kind of be working a week or two out from the experiment that we're going to start. So you've got all that good background chemistry, knowledge, and information to really understand what we're doing when we get in the lab and why we're doing it. All right. So when we start talking about a gravimetric analysis, what we're really focusing on here is a chemical reaction that's going to happen in solution. All right. So basically, I can write this as a chemical reaction. What's going to end up happening is this. We're going to end up with some calcium ion, and that's going to be an aqueous solution. And that's going to find, under certain chemical circumstances, an oxalate ion, which is C2O4, 2 minus, that's aqueous. Okay, and what we're going to end up making in this reaction is going to be a solid. So we're going to end up making this. We're going to get CaC2O4. And you actually get the monohydrate here. So it's going to have a water of hydration attached to it. So like when we calculate a molar mass for this thing, we have to make sure that we account for that water of hydration. So it's in there because we're forming this precipitate from an aqueous solution. So we actually pull up a water per formula unit when we do that. So the important thing to recognize is that this is going to be a solid. All right, so the whole purpose from a quantitative perspective is to make this solid. And the idea here is that we're capturing calcium as our analyte. Now, what's an analyte? Well, the analyte's the thing in solution I want to find. Okay, so what we're really doing is a quantitative determination of calcium. And the way I'm going to do it is I'm going to capture the calcium by coupling it to the oxalate ion to form a precipitate. Now, once we have that precipitate, we can clean that precipitate, we can dry the precipitate, and we can weigh it. And once I've got the mass of the precipitate, and I know the formula of what I made, right, that's the monohydrate there on the other side of the arrow, then I can use simple stoichiometry to get back to the moles of the calcium that were originally in solution. And then, of course, I can represent that as a concentration or however I want to discuss it. Okay, so that's the whole purpose behind this. We're trying to capture the calcium, which is the ion of interest, as a precipitate so we can isolate it, dry it, weigh it, and quantitate it. Okay, so that's what this is all about. So to really understand this, we really have to talk about how chemical reactions take place. Because the idea here, if you really think about it, is I want to make darn sure that I'm getting as much of that calcium ion out of solution as I possibly can and trapping it in the precipitate. If I leave any calcium behind, that's an error, right? That's a source of error. So what I want to do is to stack this reaction as far in my benefit as I possibly can. So let's think about this from, say, a chem bonding perspective, right? So when we talk about a reaction in chem bonding, we assume two things. We assume first that a reaction is going to go 100% from reactant to product, okay? Now, what limits the amount of product I can make? Think back to your bonding. What limits the amount of product I can make?
The amount of reactant you have.
The amount of reactant I've got, and more specifically, the limiting reactant, right? So remember, back in bonding, you do limiting reactant problems. So in our case, which one would you want to be a limiting reactant, the calcium or the oxalate?
Calcium, because it's the analyte.
Yeah, you want to try to get the reaction to go 100% to the right by using up all of the calcium. So we're going to definitely engineer this so that the calcium is the limiting reactant. And that would make the oxalate the excess reactant. Okay, so we want to make sure that we have a large excess of the oxalate ion present in the solution so that we get all of the calcium ion. Okay, so there we are, kind of throwing our bonding level knowledge at the problem here. Now, there's a couple other things that we haven't really thought about or discussed here. Now, you might remember if you, say, had an AP high school course or maybe just a really solid course of chemistry in high school, that when we really start looking closely at chemical reactions, we're kind of told or we're led to understand that a chemical reaction is a reversible process. Okay, so you ever remember or ever see a chemical reaction where maybe you used a double arrow? You guys ever seen that before?
Yeah.
I'll bet some of you have, and maybe some of you haven't. Now, here's the deal. When you see a double arrow like that, what that's doing is it's adding another layer of complexity to the reaction. Okay, so now what this means, and this is true for every chemical reaction, is that now the reaction itself is actually going to look like a dynamic equilibrium process. Okay, so this is going to be really, really important. So the reaction is actually described as a dynamic equilibrium. So what this means to us when I say a reaction is an equilibrium process is basically what the double arrow is telling me. It's really telling me that the reaction can go in both directions and it can do so simultaneously. Okay, so that might be a new concept for some of us. Usually we think of a reaction as just running from the left to the right, but I don't really think of a reaction as running from the right or the product side back to the left or the reactant side. But that can and does happen. Okay, so here's another thing to keep in mind. One thing about this course is that we're going to be learning a lot of the same stuff in quant that we learn in dynamics. Okay, so I think most of you are in dynamics right now. My seniors aren't, they've had it, but everybody else is probably in the dynamics class right now. Okay, I'm not sure what you guys are studying in there right now. I don't get to teach it this semester, but at some point, you're going to deal with kinetics and equilibrium processes. That's maybe about a third of the way into the semester, you start doing that. Okay, so this is where we really start to deal with that. So we're going to introduce a topic right now that you're not going to get to in dynamics for probably a few more weeks yet. Okay, so this is often what happens. I like to think of quant as kind of being dynamics turned on its head. So essentially, concepts you're going to learn down the road in dynamics, you're going to get introduced to now and sooner in quant, and then there'll be other concepts later on in quant that you will have already discussed and dealt with in dynamics. So this is a dynamics level concept that we're going to hit now that you guys just haven't seen yet. Okay, so here's the situation. If I think about this as a double arrow and the reaction can go in both directions, well, then how do I define the reaction as coming to completion? What do I have to kind of assume about the reaction when I say the reaction comes to completion? Because if it comes to completion, that's telling me that those concentrations aren't changing with respect to time anymore, right? I mean, that's what happens when a reaction comes to completion. You've made the amount of product you're going to make. Okay, so what does that say about a dynamic equilibrium process? I mean, how would we sort of describe that? Well, what we would say is that the process is happening in both directions, but at equal rates. Okay, so in other words, you're going to get to a point in the life cycle of this reaction where that's going to be the situation that you've got. Okay, so if I just simplify it a little bit, let's just say I have component A and it decomposes to form B, and it does so in a dynamic equilibrium process like this. Okay, the reaction is going to come to an end. So we'll say the reaction ends, and I'm going to put ends in quotes here because a reaction really doesn't end if it's in dynamic equilibrium. Basically, what this means is the reaction effectively ends when the rate of formation of product B is equal to the rate of formation, or loss if you want to think of it, of component A. Okay, now I'm not going to get into rate laws and all of this business, but I think it's just easy enough for you to see that that's going to be the situation that we're going to have, because if those two rates are equal to each other, then the concentration of A is no longer changing with respect to time, nor is the concentration of B changing with respect to time. So I'm going to end up with what we call an equilibrium mixture of those two things. Okay, so does this kind of sort of make qualitative sense to you guys at this point in terms of what I'm trying to convey here?
Yes.
Okay, perfect. And if there are any questions, just definitely yell. Okay, so you can see here when I talk about this dynamic equilibrium situation, when we say that a reaction comes to equilibrium, the reaction is effectively done. We're not going to change the amount of product that we make. Okay, but go back to my calcium example at the top here. Why do you think this might be a problem from a quantitative perspective? I mean, if I end up with an equilibrium mixture of reactants and products, what is that telling me about the calcium?
There's still going to be some calcium in the solution.
Mm-hmm. That's exactly right. You're still going to have some calcium ion in solution. Okay, because presumably you're going to have a mixture of all those components still left in the solution. So that's another thing we have to think about. We can't trap all of the calcium because we wouldn't have an equilibrium at that point anymore. But what we want to try to do is to set the reaction up in such a way that we can force that equilibrium as far toward the product side as we possibly can. Okay, and we have means of being able to do that. All right, so that's one of the things we have to think about. How would we do it when we set up the experiment? Okay, so let's get a little further into this. When we talk about an equilibrium mixture, okay, this equilibrium mixture is going to be governed by what we call the law of mass action. So I'm going to do it for a more complicated reaction here, but it'll still be generic. So let's have a reaction that looks like this. We aren't going to worry about state at this point. We can assume it's all aqueous or gas phase or whatever. Okay. So what we see here is that big A, big B, big C, big D all correspond to reactant and product identities. Little a, B, C, and D correspond to stoichiometric coefficients, and the number out in front, in other words. Okay, so what we're going to do is we're going to say that we can define what's called an equilibrium constant, and we'll come back and talk about what that specifically means here in just a bit and what it conveys to us. But essentially, I can define this equilibrium constant. That's a KEQ. That's a big K, a capital K, because later on when you talk about rates and rate constants, a little k will represent a rate constant. So this is a capital K. And here's what it corresponds to. It's the concentration. Now I'm going to put bracketed concentrations here because those correspond to molarities. So the concentration of big C raised to the little c power times the concentration as a molarity of big D raised to the little d power divided by the concentration of big A raised to the little a power times the concentration of big B raised to the little b power. Okay, so anytime you see something in a bracket like that, that corresponds to a molar concentration of a reactant or product. It's a molarity. And generally, when we do equilibrium and we're talking about solution phase chemistry, we use molar concentrations. All right. Everybody okay with me so far? Now, what then does the equilibrium constant tell me? That turns out to actually be a temperature dependent characteristic or property of a reaction. Well, take a look at it from a mathematical perspective here. If the numerator turns out to be bigger than the denominator, that tells me that K is going to be really big, right? So I could have a KEQ, for example, that's much bigger than 1. 1 would be where the numerator and the denominator are the same value, right? But what if K is much, much greater than 1? Well, that tells me that C and D are much bigger than A and B, right? And remember what C and D and A and B correspond to. These things correspond to equilibrium concentrations, and that's really important to remember. They're not initial concentrations, they're equilibrium concentrations. So it's the concentration of A, B, C, or D that we have once the reaction has reached that state of dynamic equilibrium. Okay, so it's what we have effectively at the end of the reaction. So if KEQ is much, much bigger than unity, what does that tell me about the position of the reaction at equilibrium? Is it favoring reactant or product at the end of the reaction?
Products, if it's
Definitely,
better,
definitely
bigger than
products.
1, yeah.
Yeah, if you're bigger than 1, it means the numerator is dominating over the denominator. So it tells me that C and D are much bigger than A and B. So that tells me at equilibrium, I've got a reaction where I favor the formation of the products over the reactants. Okay, so in this case, we can say products are favored. All right. So in that case, we can say that the reaction runs far to the right. Okay, so I'll often use a big arrow there just to show that the reaction's favoring the right-hand side of the arrow. Now, what if I have the opposite situation? What if I've got an equilibrium constant which is much less than unity? In that case, who's dominating? The numerator or the denominator?
The denominator meaning the reactant.
Yes, the reactants. So what does that tell me? Am I favoring reactant or product at equilibrium?
Reactants.
Yes, my reactants are favored. Good. So what that means from the point of view of my arrow is that the reaction is favoring the left-hand side instead of the right-hand side. Okay? And then the other situation is if you have a KEQ close to 1. And in that situation, it tells me that the numerator and the denominator are about the same size, right? So in that case, what have I got? I've got a nearly even or equal distribution of reactant and product at equilibrium. Okay, does that make sense to everybody? So the equilibrium constant is really important because if I go look up an equilibrium constant for a given reaction, what it's telling me is that at a certain temperature or under a certain set of conditions, it's telling me whether that reaction is going to favor the formation of product or reactant. Now, if I'm back to my quant problem where I want to generate as much product as possible to capture as much of the calcium ion as I want, what do I want my K to be, big or small for that reaction?
Big.
I want a really big K. Yeah, I want to force that reaction as far away from the calcium ion and toward the precipitate as I possibly can. So I want to make sure that I'm utilizing a reaction that has a really big equilibrium constant as I write it. Okay, so that's the meaning of the thing. And that's why it's important to us. So let me just give you a real quick example of this. So here's a reaction you're going to study actually a lot in dynamics. You're going to see this one when you deal with acid-base reactions. That's acetic acid, right? So it's the acetate ion with a hydrogen out in front. So that's acetic acid. It's aqueous. Now what we can do is we can actually write a dissociation reaction for this thing, okay? And a lot of times we'll write it with water in there because water actually takes part in the dissociation or acid-base reaction of this thing. It's a reaction here, and one of the definitions of an acid is an acid will donate a proton or a hydrogen ion to the base. So if the acetic acid is the acid, water has to be the base, so we donate a proton to it. So you end up making hydronium ion. And then you're left with the acetate ion. Okay. And just for the record, guys, this is considered to be a weak acid dissociation. Acetic acid is a weak acid. And again, if you go back to your bonding, when you talked about acids and bases in there, you probably in your lecture differentiated between weak acids and strong acids. And the definition of a strong acid is one that dissociates 100% in solution. So in other words, it really has a huge K associated with it. And a weak acid is one that just dissociates a little bit. Okay, so how do I know it's a weak acid? Well, one way I can determine that is I could look up the KEQ for the reaction as I've written it. And your book actually has it in a table. And the KEQ turns out to be 1.75 times 10 to the minus fifth. All right. Now here's another thing about equilibrium constants. They don't have units. It's one of the few things you're going to run into in chemistry that doesn't have a unit associated with it. Okay. So Notice that's a very tiny value. So what does that tell me about the position of this reaction at equilibrium? What am I favoring, reactant or product here at equilibrium?
Reactants.
Yeah, so if I wanted to, I could put an arrow above this to sort of show that at equilibrium, I have very little product and a whole lot of reactant. So another way of saying that is that the acetic acid doesn't dissociate very much. Most of it remains in the molecular form as you see it there on the left-hand side of the arrow, okay? So you end up making just a tiny amount of the hydronium ion and the acetate ion. All right, so that kind of tells us, you know, what this reaction means in terms of how much product I can make relative to how much reactant I might make. So in this case, I'm going to have a lot of reactant and almost no product. So from a quant perspective, if I'm trying to get to product, this isn't a very useful reaction, right? All right, everybody good with that so far? All right, good. So few rules that we have to keep in mind. This is kind of where we're sort of setting up the ground rules for dealing with equilibrium constants. So these are rules for understanding or writing KEQ expressions. And usually when I say expressions, I'm talking about utilizing the law of mass action here. Okay, so item number one, we've already mentioned, and that is concentrations are always going to be in terms of molarities. Big M, so that's going to be moles per liter of solution, right? Now, there's a couple other things. We don't really run into gas phase reactions here so much. You're going to run into those when you deal with equilibrium in dynamics. And if you're dealing with a gas phase reaction, you can either express it as a molar concentration because you know the size of the vessel and how many moles of the gas you have in it, or you can couch it in terms of the partial pressures of the gas. But for us, we're going to stick to molarities because in quant, we deal pretty much almost always with liquid phase solutions. So that's what we're going to stick with here. But you'll look at other options of this when you're in dynamics. All right, there's another thing to keep in mind here. Solids. And again, this is liquid solution chemistry we're talking about here. Pure liquids. And solvents don't appear in the law of mass action. All right. So, hey, let's just go back to the example I had up top. I gave you that reaction involving the dissociation of acetic acid. If I wanted to actually write that in terms of the law of mass action using molar concentrations of reactants or products, how would we do it? Here's how it would look. Products over reactants raised to their respective powers, right? So it'd be the equilibrium concentration of the hydronium ion raised to the first power because it has a stoichiometric coefficient of 1 in front of it, right? Times the acetate. Okay, that's also expressed as a molar concentration. Now, what goes in the denominator here, guys?
Acetic acid.
Yeah, sure thing. We need our equilibrium concentration of the acetic acid. So that's my HC2H3O2. Do I put water in there?
No, because
No.
it's pure liquid.
It's a pure
And a
liquid and a
solvent.
solvent. Yeah, it satisfies both of those requirements. Water is a pure liquid. So anything that has an L there, notice in my water, I have an L there instead of an AQ. That tells me it's a pure liquid, but we also know it's the solvent. So it's not going to show up in the law of mass action. So I don't put it in there. Okay. That all right with everybody? So again, those are some basic rules you have to remember when you're dealing with writing these things from balanced reaction equations. Now, there's a few other things that we have to talk about as well. One of them is, how do you manipulate KEQ values? Now, when I say this, I'm really talking about how I write a reaction, okay? So let's say I've got a reaction. I'm just going to use a generic reaction here, if I may. I'm just going to say A plus 2B is in equilibrium with its product C, okay? Could I write an equilibrium expression for that in terms of the law of mass action? And again, let's assume all of these things are in aqueous solution. Sure, I could, right? My KEQ is going to equal to the concentration of C raised to the first power divided by the concentration of A raised to the first power, also divided by the concentration of B. What do I do to B?
Square it.
I need to square it. Everybody see why I square it? That's because, yeah, it's a stoichiometric coefficient other than 1, okay? Now, here's the thing. What if, just based on making the math easier because I need to do it, or maybe because I'm interested in the reverse reaction instead of the forward reaction, what if I just write the reaction in reverse? And sometimes this is a useful thing to do. We go A plus 2B. Okay, could you write the equilibrium expression for that? Sure, you use the same rules, don't you? So now A goes to the top because now it's a product. B to the quantity squared is also in the top because it's a product, and C goes to the bottom. Okay, so I just applied the law of mass action just like I always do here. I'll call that a KEQ primed because it's obviously related to the first because it's just the top reaction in reverse. So now here's the question. Do I have a mathematical relationship between KEQ and KEQ primed? In other words, if I have my KEQ primed here, how would I write that in terms of the original KEQ? It's just the reciprocal of it, right? It's just 1 over it. Everybody see that? So that's a rule I can use. If I write a reaction in one direction and I have a KEQ for it, but then I want to flip the reaction, can I get to the new KEQ for the new reaction? Sure, it's just the reciprocal of the KEQ for the original reaction. So everybody see how that works? And again, it's just application of the law of mass action. What used to be the products are now the reactants, and what used to be the reactants are now the products. Does that make sense to everybody?
Yep.
Okay, good. Now there's another rule we have to remember. And sometimes we find out, and when we work equilibrium type problems, which we will do sooner than later, that sometimes we have multiple reactions and we have to end up adding those reactions together, maybe to get to a target reaction. Kind of like we used to do, remember Hess's law that you guys did last semester when we dealt with thermochemistry? So you could write a series of reactions and then you could manipulate them and add them together to get an overall delta H of your new reaction. Well, we kind of do similar kinds of things when we work equilibrium problems. So we have rules for adding reactions together. Okay, so let's just, again, come up with some simple generic reactions here. I'll start with the one I had before, A plus 2B go into C. And then I'll add a new one that involves C. We'll say once we make C, we can say that C will combine with D and we'll end up making, let's say, E. Okay, so I have 2 reactions here. Now I can write a KEQ expression for each one of these reactions. So let's just do it so we can see where this comes from. Products over reactants raised to their respective powers. Okay, so you guys verify. I'll get C on the top, I'll get A on the bottom, and then I get B squared also on the bottom. It should be B to the quantity squared. There we go. Everybody okay with that? Now I could do the very same thing for the second reaction down here. Just again, applying the law of mass action. So I'm going to get E on top, right? And now I'm going to get C on the bottom, and I'll get D on the bottom, all raised to the first power. Everybody okay with that? Now, let's add the two reactions together and just see what we get. Okay, so notice what happens. Who cancels out when I add the reactions?
C.
C. Okay, so C's cancel both sides. So what I'm going to end up getting is A plus 2B plus D going to E. Did I do that right? I think I did that right. So now let's write the law of mass action for that, just based on the reaction I got. Okay, so I'll call that a KEQ1, KEQ2, and KEQ3, so I can just keep track of all of them here. So it seems like I got E on the top here, raised to the first power, and I got a whole bunch of stuff in the denominator. It's like I've got an A raised to the first power there, I've got a B raised to the second power there, and I got a D raised to the first power. Did I do that right? So here's the question I would have for you. How can I combine KEQ1 and KEQ2 to get KEQ3?
Multiply the fractions.
I'm going to end up, yeah, actually doing exactly that. I'm going to end up multiplying the two together. So let's do that. So we'll say KEQ1 times KEQ2 should give you KEQ3. So let's verify that that does indeed happen. Okay, so I've got a C. This is just subbing in KEQ1 there over an A, and I got a B squared. Now I want to multiply that by KEQ2 in terms of the law of mass action. So I got an E, and I got a C, and I got a D. Okay, so again, what happens to C? C cancels, right? And now let's just write out what we got left. So I got an E in the top. Okay, again, these are all equilibrium concentrations. Over, it looks like an A. I still got a B squared in there. And now I got a D. Now, did that give me my KEQ3 back again? Yeah, it looks like it did. Okay, so we just did a simple little proof there that shows that if I add chemical reactions together and I have equilibrium constants for the two chemical reactions that I want to add together, and I want to get the equilibrium constant for the summed reaction, I do it by just multiplying together the equilibrium constants of the added reactions. Everybody see that? So again, just another simple rule you can use, and this comes in handy down the road. Again, when we have to add reactions with known K, so I can derive a K for a new reaction, which is the sum of the two that I want to add together. Everybody okay with that? So again, what I'm generating here is essentially toolkit stuff. So this is stuff that we're going to kind of put away in our memory banks, and we're going to pull it out when we need it, when we start problem solving. All right, questions? All right, now there's another really, really important concept that I want to bring up here. So again, it's part of our toolkit that we can use as we manipulate reactions and try to, force things in the direction we want them to go for the best quantitative result. And this is something called Le Chatelier's principle. And we're dealing with an equilibrium system here, okay? Now, basically what Le Chatelier's principle says is that if you've got a reaction and it's at equilibrium, it's gonna stay at equilibrium, okay? Unless you apply some kind of a stress to the reaction. And if you apply a stress of some sort to that reaction, the equilibrium position will change to alleviate the stress, okay? That's what Le Chatelier's principle says. Okay, so we'll just start by saying when a stress, and we'll define in a moment what a stress is applied, to a reaction at equilibrium, the equilibrium will shift. We'll say the equilibrium position. To alleviate the stress. All right. So let's, for example, go back to my generic reactions so we can kind of talk about this in terms of what kinds of stresses we could apply in the quant lab to kind of move things, say, in the direction we want them to go. So we'll go back to A plus 2B in equilibrium with its product C. Okay, and again, I can write a KEQ for that based on the law of mass action. So that's going to be your concentration of C over your concentration of A over your concentration of B to the quantity squared. Okay. Now here's the deal. If I've got a system at equilibrium here, the position of the equilibrium is going to be defined by the size of KEQ, right? So that's going to define my distribution of reactants and products that I have at equilibrium. So there I am. I'm at equilibrium. I haven't applied any kind of stress. Now, when I say a stress, what I'm really talking about is some sort of change to the reaction that knocks it out of equilibrium. So there's lots of things I could actually do here. So one type of stress I could apply might be adding a reactant, or maybe another one might be removing a product or removing a reactant. Okay, these are all stresses that I could apply. Okay, so let's say, for example, I want to add some A. Okay, now if I add A, notice what happens to the law of mass action, right? What happens to the A in the bottom? Well, it gets bigger, doesn't it? The A in the bottom gets bigger. So what happens to KEQ if A gets bigger? Does KEQ get smaller or bigger?
Smaller.
It gets smaller. Okay, so now I've knocked the system out of equilibrium, and now my KEQ is no longer my KEQ. That law of mass action is now a smaller number. Okay, so here's the question. To make that smaller number bigger so I can get back to the original equilibrium again, which way does the reaction have to go? In other words, which way does the reaction have to shift? Toward product or away from product to make that happen?
Away from product.
Careful, watch out, because I just made this bigger, right?
It'd be toward product.
Yeah, if I just made that bigger, my new, and I'm going to call this a Q instead of a K, because it's no longer an equilibrium constant, because now I got to get back to equilibrium. So now we call this a reaction quotient. So now my Q is less than, sorry, I got to remember which way the alligator's mouth opens here, right? Is less than my KEQ. Everybody see that because I made A bigger? So now I want to make my Q equal to my K. So if Q is too small and I want to make it K again, I need to make C bigger and A and B smaller, right? In other words, I need to have more numerator and less denominator. Does that make sense to everybody? I want to make my Q equal to my K. So to do that, I have to make my numerator bigger and my denominator smaller, right? If Q is less than KEQ. Does that make sense to everybody?
Yeah.
So how do I make my numerator bigger and my denominator smaller? Which way does the reaction have to go?
Towards the product.
Towards the product. So I'm going to see a shift towards the product to reattain equilibrium. Okay. So that's Le Chatelier's principle working for us. Now, why does this matter to us in the quant lab? Well, again, we want to hedge the bet as much as I possibly can. So say C is the precipitate I want to make, and A, of course, is going to be the reactant that's my analyte, right? or maybe B is. It doesn't really matter which way you do it. Usually I don't want to mess with the analyte concentration, right? So let's say B is the analyte. Okay, and I added A. What am I doing? Well, if I add more A, I'm using up more B and turning it into the precipitate C. Okay, so I'm trapping more of the precipitate that way by forcing the equilibrium further to the right. Or I should say the position of the reaction further to the right. Does that kind of make sense to everybody? What if I, let's rewrite it another way. Let's just say I can go this way as well. Let's say use the same reaction. So let's say in this case, I'm going to remove some C. Take some C out. Okay, so again, let's do this in terms of the law of mass action. My KEQ is equal to C divided by A times B to the quantity squared. Now, if I remove C, what's happening to the numerator? It's looking like it's smaller, right? I just took some C out, so the concentration of C is getting smaller in my equilibrium mixture. Now, what does that tell me about my Q? Now, in this case, again, if C is smaller, I've got less numerator per denominator. So is my Q less than or equal to my KQ in this case?
Equal to?
Not equal, because I took some C out, right?
It's less than
So we
again, right?
Less than. I'm still less than, right? I'm still less than. In other words, I made the numerator smaller relative to the denominator. So in this case, I'm still less than. So tell me, if I remove some C, which way does the reaction have to go to reattain equilibrium so that my Q is equal to my K? Which way do I have to go?
Towards the reactants?
Now, if I go towards the reactants,
Yeah,
I'm making C
product.
smaller and the other stuff bigger, and that's going to exacerbate my problem, isn't it?
Yeah, product,
Yeah.
sorry.
No, that's okay. That's why I like you guys answering this, so we can kind of think it out. So which way am I going to need to go?
Towards the products.
Towards the product. So again, the whole purpose here to make my Q equal to my K, it's the same problem I had before, right? I need to make more C and use up some A and B. And that readjusts that ratio so that now my Q will be equal to my KQ. And that's how I get back to my equilibrium position. So that would be another way to drive the reaction back toward the product side. Okay, does that make sense?
Yeah.
Good. All right. So I think we're close to out of time here, guys. But what I'm trying to do here, again, in this little bit of a lecture that we had, is I'm trying to kind of give you the tools that we're going to need to really get into equilibrium problems and then learn how to apply that kind of problem to actually maximizing the yield of a product in a reaction. Like, for example, the formation of our precipitate that we're going to make that's going to contain our analyte. All right, so here's all the tools in the toolkit. So what we're going to do on Monday, because we're at Wednesday now, right? What we're going to do on Monday is we're going to actually talk about a very specific kind of equilibrium that involves the formation of precipitates. Okay, so what we're going to find when we deal with equilibrium constants is there's all sorts of different kinds depending upon the kind of reaction we're dealing with. So we're going to deal with one that involves precipitates. So that's where we're going to start on Monday, and we'll work some problems involving that kind of equilibrium constant, and then how to, for example, predict what equilibrium concentrations might look like. All right, any other questions, guys? Okay, make sure to visit D2L. There's already some stuff there in the homework you can start on, because a couple of the problems just deal with simple equilibrium stuff. And then I think a couple of them deal with actual precipitations. So that'll be Monday stuff. So we'll see how far we get on Monday, but you can at least start the homework and make sure you're prepping your notebook for next week, guys. All right, anything else? Everybody good? All right, I'll see you guys on Monday then.
Have a good day.
All right, thanks. You too.